Alright, this video is intended to be an introduction to titration. You guys did a titration last year in Honors Chem, so really we're kind of reviewing and then we're going to add some calculations to what you did last year. First and foremost, the definition of a titration is basically where you take a known concentration of something and you add it to an unknown concentration so you can figure out the concentration of the unknown. So you basically use a known to find the concentration of an unknown concentration. Titration is basically what you're going to do. The definition of equivalence point. That is the point at which the reaction is complete, and I'll come back to that. We'll do a little bit more detail. You remember from last year, probably if your flask turned very, very pink, we use indicator solutions that change color at the end point. The end point is where we stop the titration. When we get a color change that we're looking for, that represents the end point. So the idea is you have a known concentration, which will be in the burette, which you see here, and you're putting it into an unknown until you get a color change, and then based on that, we did a redox titration actually before, I just remembered. So if you remember a redox titration, the same idea. So if you look here, key thing when we're talking about acids and bases is we're looking towards neutralization. A neutralization reaction is when you combine an acid and a base, and you try and figure out what the equivalence point is. Equivalence point means that the moles of the acid equal the moles of the base. They cancel each other out. So at that point, at equivalence, they've canceled each other out, and then that's when you have equivalence. Now, what does equivalence point really mean? Well, imagine I have an acid down here. Here's an acid. I'm not sure how many H's are in there that are going to make up my concentration, but I just drew 6 H's, right? And then in my burette, I have a base, which is OH minus. And I know exactly what my concentration of my base is. How many OH minuses per milliliter? I can calculate it out. So what happens when we do a titration is you're going to add an OH, and OH drops in. You get HOH, and you make water. So you turn that into a water molecule. There's 1. Then I drop another OH in, 2, 3, 4, 5, 6. At that point, the moles of the H plus equal the moles of the OH minus. That is equivalence. If I put 1 more OH in from my burette, drop it in there, if I have an indicator, the solution changes color, which will allow me to figure out what the molarity of the unknown concentration is. In AP Chem, you have to be able to calculate the molarity of the unknown concentration. You have to be able to calculate the pH at any point in the titration. So that's basically what we're going to kind of focus on. That's what equivalence means when we talk about it. Now, you guys remember from before, a burette, basically the known concentration goes in the burette. You're going to fill it up. You can read a burette is a volumetric marking device which dispenses, it's marked, dispenses exact amounts through the burette. And then usually in your setup, we're going to do these in a week or so, you'll have a pH meter in there which will allow you to track the pH as you go. That's a typical setup. So there's volume markings on the side of a burette that's used. The stopcock opens and closes, which allows you to dispense whatever's in there. Typically it's a base, but it could be an acid. All right, when we talk about tomorrow, we're dealing with the strong acid, strong base titration. Pretty much in all titrations, there's 3 parts. There's the part that is before equivalence. So stage number 1, like if you plot a titration curve, is before equivalence. This is the area represented by 1 right here. That's basically dominated by the presence of, in this case, an acid, because see, we started at a low pH. So this is a strong acid, strong base titration. So part 1 is before equivalence, pretty much the acid's there. You're adding OH, but it's not really canceling anything out. Then you see region 2. Region 2, in the center of it, is at equivalence. That's when the acid and the base are equivalent. You basically reach an equivalence point, which will be somewhere in the vertical area. Notice there's a quick change, the pH. As you add a little bit, it skyrockets in that vertical section. That's going to be right around equivalence point. In fact, halfway up in that vertical section allows you to figure out what the equivalence point is going to be. The third section is after equivalence. After equivalence, actually I should write EQV versus, looks like equilibrium, EQV. After equivalence. After equivalence is going to be represented by the region up here on the titration curve. Right there, basically after equivalence, the thing that's going to set the pH is the fact that you're adding OH minus or a base, which is going to be the thing that's going to determine what your pH is. Notice on a typical pH or a titration curve, in this case, since we're titrating with a base, the volume of the base is here. the pH value is listed there. So the key three parts. You have before equivalence, which is basically the pH is going to be determined by how much H plus you have. That's the key thing that you need. At equivalence, H plus and OH minus are equal to each other, so your pH is basically going to be 7. After, you're going to have extra OH, which is going to be the thing that's going to set your pH. So it's important to know the 3 stages of a titration. Now, one of the key things that we've used before in other chapters that's coming back is you have to be able to find moles, because in chemistry we relate moles to each other. Whenever we need moles of anything, you take molarity times liters will always get us moles. Always. You have to remember that. That's key for especially this chapter. So, if you look right here, titration of 20 milliliters of HCl acid is solution needed 5 milliliters of 0.52 NaOH to reach the equivalence point. First question they're asking is how many moles of NaOH were added? In case you need to calculate moles, I have milliliters and molarity. So all I would do is go 0.52 times, that's my molarity times liters. In this case, my liters is going to be 0.005. That's going to be liters right there. Molarity times liters is going to be equal to 0.0026 moles of OH minus. That's how many moles of OH minus you're going to add. So whenever you need to calculate moles, tomorrow when we're calculating moles, remember we get moles times M times L always gets us moles. Now you may remember the neutralization equation. We talked about neutralization or equivalence. Well, we know that the molarity and the volume of a base, in this case we know we have 0.0026 moles of OH. This is the equation you guys used last year to find neutralization. Since this is NaOH and there's only one OH, this technically is 1 here. If I have 0.0026 moles of OH, guess how many moles of H plus if I know it's at equivalence? Because I said I reached equivalence, means I have to have 0.0026 moles of H plus present there. Now, that's not exactly how you guys did the calculation last year. What you guys did is you typically you would do this when you did this calculation. You would look up here, and you would take the 20 milliliters of HCl, the volume of the acid, 20.0 ml goes there. You're solving for X, the molarity of the acid. Since it's HCl, there's only one H, so that's going to get a 1 there, equals molarity of the base is 0.52 molar, and then the volume of the base is 5.0 milliliters. No need to change it because I'm trying to solve. If I'm solving for X in this case, I'm finding molarity. And then this is equal to 1 as well. So ultimately, to get the answer, I'm basically going to just go 0.52 times 5 divided by 20. What I end up getting when I do that is X becomes 0.13. So that's my concentration of, or my molarity of the acid. And that's a calculation that, one of the calculations we do with titrations, because that's a calculation around equivalence point. Now, tomorrow, we're going to use what's called a Bacam table. A Bacam table is using the stoichiometry of an acid and a base reacting to figure out what the molarity is when the reaction happens. So when we go to do a Bacam table, the equation goes on top. The B in Bacam stands for before, how many moles you have before. So for example, let's say I started out with an acid that had 0.02 moles. Well, to get the moles in here, I'm going to have to take molarity times liters of each of the things I'm given in the problem. Added means whatever you're titrating with. In this case, if I'm adding OH, the added, let's say I add 0.01 moles there. Then the relationship between these two will tell me what the limiting reactant is. In this little box, the smaller number is automatically going to be my limiting reactant. Remember change from equilibrium? We don't use X this time. What we're going to do is we're going to pick the smaller number in the box. Whichever number is smaller, in this case 0.01, means I'm going to go minus 0.01, minus 0.01, plus 0.01, because all the coefficients are 1. So it's basically like minus X, plus X, except in this case we have the moles, so we know we can figure out the limiting reactant. After just means canceling out the moles, meaning subtracting the change line from the line above. So 0.1 minus 0.1, I would have 0 amount of OH left. 0.02 minus 0.01 means I would have 0.01 moles of H plus left. So I know I'm actually before equivalence because I still have H left over. The last step in a Bacam table is you have to calculate out the molarity. A key thing to remember is down here. Whenever you're going to calculate out the molarity on a Bacam table, you have to use the new volume, because what's happening is you're combining, let's say we happen to combine in this case 10 milliliters of one versus 10 milliliters of the other would be given you in the problem. The new molarity, or the new volume in that case, you would divide it, would be divided by 0.020 liters. Because when we get molarity, it's moles over liters. So the point of a Bacam table is for us to get moles, the moles remaining on the after line, and the other key thing we want to do is always divide by the new volume. Then once we get the molarity of H+, we can easily find pH, because that's the idea in a strong acid, strong base titration, is you're ultimately trying to find the pH of the solution. Before equivalence, at equivalence, and after, because those are the three regions in the chart. So when we come back here, let me clear this off. There's three types of calculations in a Bacam table. Before equivalence, at equivalence, and after. Key things we have to be able to do is we need moles for everything in a Bacam table. So molarity times liters. And when we get our Bacam table, the first thing that we're going to do is we're going to pop the moles in here. The moles are what we start with. The moles are what we're adding. From that point on, it's just basically like a little bit of stoichiometry. It's a little bit of stoichiometry in a table, or in a Bacam table, basically, is the way it works. And in the end, you calculate new molarity by using the moles that you have remaining, either one of these moles, because the water doesn't matter, because water doesn't affect pH. But if you have H+ or OH, that's ultimately what we're solving for when we use a Bacam table. All right? Make sure you save your notes in case I quiz you on this tomorrow at the beginning. Key things you need to know are what the Bacam table means. You have to focus on the new volume. You should also know that molarity times liters gets you moles. Another key thing is the definition of equivalence. When we talk about equivalence, it means the moles of the H+ and the moles of OH are equal. At that point, we reach equivalence point. Hopefully, the end point or the color change will be right after. All right? There's a sheet of notes you need to bring with you, too. See you tomorrow. Thanks.